The universe is supposed to be predictable, governed by equations, balanced by laws we believe we understand. But scattered across the cosmos are observations that shouldn't exist. Patterns that align when they shouldn't, objects that are older than time itself, structures too large to form. Tonight, we explore 50 space mysteries that suggest something disturbing. Our understanding of the universe may be fundamentally wrong. These are the cracks in reality. Part 1, Cracks in the Sky. When the universe was young, it left fingerprints, but some of those fingerprints don't belong. The cold spot hangs in our sky like a bruise on creation itself. It's a massive region in the cosmic microwave background radiation, colder than it should be, larger than our models predict. Nearly 1 billion light-years across, this void challenges everything we thought we knew about the universe's birth. When we map the afterglow of the Big Bang, we expect to see tiny temperature variations, ripples frozen into the fabric of space at the moment of cosmic inflation. These ripples should be random, distributed evenly across the sky, following the quantum fluctuations that seeded all structure in the universe. The cold spot doesn't follow these rules. It's too cold, too large, and too void-like. Some cosmologists suggest it might be a supervoid, an enormous empty region of space that leaves a cold imprint through the integrated Sachs-Wolf effect. But even this explanation requires stretching our models to their breaking point. Others whisper about more exotic possibilities. Collisions with parallel universes during the inflationary epoch, imprints from before the Big Bang itself, echoes of a previous universe that collapsed to birth our own. The mathematics work barely. The probability is vanishingly small, yet there it sits, undeniable, a scar on the sky that shouldn't exist. Then there's the asterisk axis of evil asterisk. Scientists gave it that name for a reason, half joking, half serious about the implications. When we mapped the oldest light in the universe with increasing precision, we expected chaos, randomness, the fingerprint of quantum foam expanding into spacetime. Instead, we found alignment. The largest temperature fluctuations in the cosmic microwave background line up with each other and with the plane of our solar system. The quadrupole and octupole moments, the largest scale patterns in the cosmic microwave background, share a common orientation. They align with the ecliptic, the plane in which Earth orbits the Sun. The odds of this happening by chance are astronomical, yet here we are, at the apparent center of a cosmic pattern. It's as if the universe knew we were here, as if it pointed directly at Earth. This violates the Copernican principle, the foundational assumption that we occupy no special place in the cosmos. For centuries, science has worked to dethrone humanity from the center of creation. First, we learned Earth orbits the Sun, not the reverse. Then we discovered our Sun is one of billions in a galaxy that is itself one of billions. We are supposed to be insignificant, average, unremarkable. The axis of evil suggests otherwise. It suggests that either we are cosmically special in some way we don't understand, or our models of the early universe are missing something profound. Why does randomness keep forming patterns? The cosmic microwave background should be a canvas of pure chance, the afterglow of creation settling into white noise. Quantum fluctuations during inflation should have seeded irregularities that are statistically random, following probability distributions we can calculate precisely. But everywhere we look, we find structure, alignment, purpose where there should be none. Hot spots and cold regions form geometric relationships that shouldn't exist. Patterns emerge at angular scales that imply coordination across billions of light years, across distances so vast that no signal could have traveled between them even at the speed of light. These regions have never been in causal contact, yet they correlate. Inflation theory was supposed to explain everything. A split second of exponential expansion, a period where the universe doubled in size every fraction of a second, stretching quantum fluctuations to cosmic scales. This mechanism should have smoothed the universe, erased the wrinkles, created the homogeneous cosmos we inhabit. The theory has been incredibly successful, predicting the detailed structure of the cosmic microwave background with remarkable accuracy. But inflation cannot explain these alignments. It cannot explain why patterns emerge at the largest scales when they should be random. It cannot explain why the universe remembers directions, why it preserves relationships across impossible distances. Either inflation happened differently than we think, or something else happened before inflation, something that imprinted structure onto the cosmos before expansion began. Some theorists propose that the universe had a pre-inflationary phase, a period of existence we cannot observe, but that left subtle fingerprints. Others suggest inflation itself might be more complex, involving multiple fields or directional properties we haven't accounted for. Still others wonder if these anomalies are statistical flukes, unlikely but not impossible, the kind of patterns you find if you look at enough data. But the patterns persist. They deepen with better observations, and they suggest that the first moments of cosmic time were stranger than our best theories allow. The universe is moving, but why? If everything expands evenly, why does the universe seem to lean? Dark flow asterisk is motion on a scale that shouldn't exist. Galaxy clusters, hundreds of them spanning a region of space over 3 billion light-years across, all moving in the same direction at over 2 million miles per hour. Not away from each other, as cosmic expansion predicts. Not randomly, as individual gravitational influences suggest. Together, coherently, as if pulled by something beyond the edge of everything we can see. This flow was discovered by analyzing the kinematic Sunyaev-Zeldovich effect, tiny temperature variations in the cosmic microwave background caused by galaxy clusters moving through space. When scientists mapped these motions, expecting to see random velocity patterns, they found instead a coherent bulk flow. Galaxy clusters across vast distances share a common motion, drifting together toward a region of space in the southern sky. The discovery was controversial immediately. Other teams tried to replicate it and found conflicting results. Some confirmed the flow, others found nothing, still others measured flows in different directions. The debate continues, but if dark flow is real, the implications are staggering. This flow extends beyond our cosmic horizon, pointing toward something we cannot see and may never be able to observe. The observable universe has an edge, a boundary imposed not by walls, but by time and the speed of light. Light from beyond, this boundary hasn't had time to reach us yet. We are trapped inside a sphere of visibility, and dark flow suggests that something beyond that sphere is massive enough to influence galaxies on our side. The region toward which everything flows has been called the Great Attractor asterisk, though this name predates dark flow and refers to a more local phenomenon. The Great Attractor is a gravitational anomaly in the direction of the constellations Triangulum, Austral, and Norma, hidden behind the plane of the Milky Way. Our galaxy and millions of others are falling toward it at hundreds of kilometers per second. For years, we couldn't see what was there because the dust and stars of our own galaxy block the view. Finally, surveys in other wavelengths penetrated the zone of avoidance and found it. The Norma cluster, the Great Attractor cluster, massive concentrations of galaxies pulling on the local group with inexorable gravity. But the Great Attractor itself is falling toward something else. The Shapley supercluster, a massive concentration of galaxies 650 million light-years away, pulls on both our galaxy and the Great Attractor. Layer upon layer of invisible gravity, mass we cannot see pulling on mass we can measure. Hundreds of millions of solar masses concentrated in regions our telescopes still struggle to penetrate. The implications are profound. The cosmological principle, the assumption that the universe is homogeneous and isotropic at the largest scales, is one of the foundational pillars of modern cosmology. It tells us that the universe has no center, no preferred direction, no special places. Dark flow and the Great Attractor suggest otherwise. If there's something beyond the observable universe massive enough to influence galaxies on our side of the cosmic horizon, then our universe is smaller than we thought, or more connected. Or both. The cosmic web we map so carefully, the filaments and voids and superclusters, may be just one neighborhood in a city we cannot comprehend. Perhaps the observable universe is like a bay on an ocean we'll never cross. We see the water we can reach, map the currents in our local region, but remain ignorant of the continents beyond the horizon pulling the tides. These asterisk structures violate the cosmological principle asterisk in ways that make cosmologists uncomfortable. The principle isn't just a nice idea. It's mathematically embedded in general relativity, in the Friedmann equations that describe cosmic expansion, in every model we use to understand the universe's evolution. If the universe has large-scale flows, preferred directions, regions of significantly enhanced density that extend beyond our horizon, then these models break down. Some argue that the cosmological principle only applies at the very largest scales, scales beyond those where we see these anomalies. Others suggest we need to modify our understanding of cosmic expansion, incorporating bulk flows and large-scale inhomogeneities into the standard model. Still others wonder if dark energy itself might have directional properties, pushing harder in some directions than others. The universe, it seems, has geography we were told couldn't exist. It has currents and rivers, attractors and repulsors, structure at scales where everything should smooth out into featureless uniformity. And the most unsettling part is that we're moving through it, caught in flows we didn't know existed, falling toward destinations we cannot see. Part 3. Structures that should not exist. At this scale, coincidence stops being an explanation. The asterisk giant arc asterisk stretches across 3.3 billion light-years of space, visible in the distribution of magnesium absorption systems in quasar light. It's a curved formation of galaxies and galaxy clusters, one of the largest coherent structures ever discovered, apparent in sky maps as a graceful arc of matter crossing an enormous swath of the cosmos. According to our models, structures this large cannot form. The universe hasn't existed long enough. Gravity doesn't work fast enough. There simply hasn't been enough time since the Big Bang for gravity to pull together galaxies across such vast distances into coherent formations. The end of greatness is a principle in cosmology, the theoretical scale beyond which the universe should appear smooth and featureless. Beyond a certain size, roughly 1.2 billion light-years, structures should dissolve into statistical uniformity. The cosmic web should fade into homogeneity. The giant arc exceeds this limit by nearly a factor of 3. And it's not alone. The Sloan Great Wall asterisk, discovered in data from the Sloan Digital Sky Survey, stretches for 1.4 billion light-years. The huge large quasar group asterisk contains 73 quasars spread across 4 billion light-years. The asterisk giant GRB ring asterisk, visible in the distribution of gamma-ray bursts, spans 5.6 billion light-years in diameter. Each discovery pushes the boundaries of what should be possible. Each structure requires more time to form than the age of the universe allows, more coordination than random gravity can provide. These are not loose associations of galaxies, not statistical flukes of data analysis. They are coherent structures with defined shapes, boundaries, and orientations. The mathematics of structure formation are well understood. Small density fluctuations in the early universe grow over time as gravity amplifies them. Regions slightly denser than average pull in surrounding matter, growing denser still, eventually forming galaxies and clusters. The process is slow, constrained by the expansion of space and the finite speed at which matter can fall together. At cosmic scales, the growth rate becomes even slower. Structures larger than a certain size simply don't have time to collapse into coherent formations within the age of the universe. The giant arc and its siblings violate this constraint. They exist, therefore either our understanding of gravitational collapse is wrong, or these structures formed through mechanisms we haven't discovered, or they're not structures at all but cosmic mirages, projections of smaller objects that happen to align in our view. The last explanation is the most comforting but the least likely. The statistical analysis is solid. These are real overdensities, real concentrations of matter, not optical illusions. Hoag's object asterisk stares back at us like an eye, a perfect ring galaxy nearly circular in shape. At its center sits a spherical core of older yellow stars. Surrounding it, separated by a gap of near-perfect darkness, is a detached ring of young blue stars still forming in clouds of gas and dust. The symmetry is eerie, the separation too clean. ring galaxies can form from collisions. When a smaller galaxy punches through the disk of a larger spiral, it can send shock waves rippling outward, compressing gas and triggering star formation in an expanding ring. The process is violent, messy, leaving debris and distortion in its wake. Hoag's object shows no signs of disturbance. Its core is relaxed and symmetric. Its ring is too circular, too uniform. No obvious collision partner exists nearby. The conventional explanation struggles to account for what we see. It sits there, defying categorization, a cosmic archway to nowhere. Even stranger, inside the gap between the core and the ring, if you look closely enough at deep images, you can see another ring galaxy in the background, billions of light years farther away. A ring galaxy inside a ring galaxy, aligned by pure chance. The odds are incalculable, the coincidence almost mocking. Then there are the **aligned quasars, discovered by analyzing polarization data from the Sloan survey. Quasars are the brilliant hearts of young galaxies, supermassive black holes consuming vast amounts of matter and radiating energy that outshines their entire host galaxy. When matter spirals into a quasar, it forms an accretion disk, a rotating structure that gives the quasar an orientation, an axis of rotation. These axes should be random. Each quasar forms independently, billions of light years from its neighbors. There's no reason for their orientations to correlate. Yet when astronomers studied large samples of quasars, they found unexpected alignment. Quasars separated by billions of light years, their rotational axes pointing in similar directions across vast cosmic distances. They've never communicated. Light hasn't had time to travel between them. Yet across the early universe, these cosmic beacons share an orientation, as if choreographed by forces we don't understand. The effect is subtle but statistically significant, persistent across multiple surveys and independent analyses. Explanations involve large-scale magnetic fields threading through the cosmic web, or correlations in the angular momentum of dark matter halos imprinted during cosmic inflation. These are not satisfying explanations. They require adding new physics, new fields, new mechanisms to preserve our models. The alternative is admitting that the universe has structure and correlation at scales where everything should be random. At a certain scale, coincidence loses meaning. When you have enough coincidences, enough patterns, enough violations of what should be statistical uniformity, you have to consider that maybe it's not coincidence at all. Maybe the universe is trying to tell us something. Maybe the laws we think govern cosmic structure are incomplete, missing variables, blind to forces that operate at the largest scales. Or maybe we're seeing the echo of something that happened before the Big Bang, boundary conditions imprinted on our universe by whatever came before, patterns frozen into existence at the moment of creation. The early universe grew up too fast. It's as if the universe skipped childhood. The James Webb Space Telescope has shattered our timeline. Designed to peer deeper into space and farther back in time than any previous instrument, JWST was supposed to show us the first galaxies forming, primitive and irregular, the cosmic dawn of structure. Instead, it revealed a universe that was already mature. Everywhere it looks in the early universe, just a few 100 million years after the Big Bang, JWST finds galaxies that shouldn't exist. Massive, mature spiral galaxies with defined structures, organized rotation, complex morphologies. These aren't the clumpy, irregular proto-galaxies our models predicted. They're fully formed systems that look like they belong in the modern universe, not the cosmic dawn. JWST R1* is a massive disk galaxy observed at a redshift corresponding to just 250 million years after the Big Bang. It has a stellar mass comparable to the Milky Way, organized spiral arms, and a well-defined structure. According to standard models, it takes billions of years for galaxies like this to form. The universe itself was only 1/4 billion years old. There simply hasn't been enough time. The numbers don't work. Stars take time to form from collapsing clouds of gas. They take time to burn, fusing hydrogen into helium, gradually enriching the interstellar medium with heavier elements. Massive stars live fast and die young, exploding as supernovae after just a few million years, but lower-mass stars like our Sun can burn for billions of years. The presence of old stellar populations in these early galaxies implies multiple generations of star formation, cycles of birth and death happening impossibly quickly. Galaxies take time to assemble, to settle into stable configurations. In the Standard Model, structure forms hierarchically. Small dark matter halos collapse first, gathering gas that forms the first stars. These small galaxies then merge to form larger ones, a process of gradual assembly that takes billions of years. Large spiral galaxies like those JWST observes should be late-forming systems, the products of countless mergers and accretion events. Yet JWST shows us galaxies that appear to be billions of years old existing in a universe less than a billion years old. The galaxy assembly line ran faster than we thought possible. Even more disturbing are the ** supermassive black holes **. At the center of nearly every large galaxy sits a supermassive black hole, a gravitational monster containing millions or billions of times the mass of our Sun. The relationship between these black holes and their host galaxies is well established in the modern universe, a correlation so tight it suggests black holes and galaxies grow together, co-evolving through cosmic time. JWST has found supermassive black holes at redshifts corresponding to less than a billion years after the Big Bang. These aren't just any black holes. They're billion solar mass monsters, already fully grown, already powering brilliant quasars that outshine their host galaxies. Black holes grow by consuming matter, but there's a limit to how fast they can eat. The Eddington limit describes the maximum luminosity and accretion rate a black hole can sustain. When matter falls toward a black hole, it heats up and radiates energy. This radiation exerts pressure on the infalling matter, pushing it away. At the Eddington limit, the outward radiation pressure exactly balances the inward gravitational pull. Accreting faster than this becomes difficult because the black hole's own light blows away its food supply. Even accreting at the Eddington limit constantly, a black hole takes hundreds of millions of years to grow from stellar mass to supermassive. These early black holes exceed that limit. They're too massive, too soon. Either they accreted faster than physics allows, or they didn't start from stellar mass. This has forced cosmologists to consider ** direct collapse black holes **, massive black holes that form instantly from pure hydrogen clouds, bypassing the entire stellar evolution process. In the Standard Model, black holes form from the collapse of massive stars. A star burns through its fuel, its core collapses, and if it's massive enough, it forms a black hole of a few to a few dozen solar masses. Direct collapse requires special conditions: pristine hydrogen gas, no heavy elements to cool the cloud efficiently, an intense radiation field to prevent fragmentation. Under these conditions, a gas cloud can collapse directly into a black hole of thousands or even millions of solar masses without ever forming stars. It's an elegant solution to an impossible problem, but it's also highly speculative. The conditions for direct collapse are rare, requiring fine-tuned environments that may not exist often enough to explain the abundance of early supermassive black holes. Yet here we are, forced to invoke exotic formation mechanisms to explain what JWST sees. The universe seems to have found shortcuts we didn't know existed, pathways to complexity that our physics cannot map. Either the early universe was radically different from our models, hotter or denser, or more efficient at forming structures, or something fundamental about black hole growth and galaxy assembly is missing from our theories. Every new JWST observation adds to the crisis. Mature galaxies at redshift 10, 12, 14, supermassive black holes at cosmic dawn, dust and heavy elements appearing generations before they should. The data is incontrovertible. The universe grew up too fast. Time itself might be wrong. What if the clock we use to measure reality is broken? The early dust paradox * confronts us with an impossible observation. Dust shouldn't exist in the early universe. Dust is composed of heavy elements: carbon, silicon, oxygen, iron, elements forged in the cores of stars and scattered into space when those stars die. First-generation stars, population III stars formed from pure hydrogen and helium, must live out their entire lives before dust can form. This takes hundreds of millions of years at minimum. Yet JWST has detected massive quantities of dust in galaxies observed less than 1 billion years after the Big Bang. Not just trace amounts, but enough dust to absorb significant amounts of starlight, to redden the spectra of these early galaxies, to indicate complex chemistry already at work. Either stars in the early universe lived and died impossibly fast, going through full evolutionary cycles in timescales that violate everything we know about stellar physics, or our understanding of stellar timescales is fundamentally flawed. Or perhaps there are non-stellar sources of dust we haven't considered, mechanisms for creating heavy elements that bypass star formation entirely. Then there's the Methuselah star asterisk, officially designated HD 140,283. It's a subgiant star located about 190 light-years from Earth in the constellation Libra, visible through modest telescopes, unremarkable in almost every way except one: its age. When we measure its age using stellar evolution models, comparing its temperature, luminosity, and chemical composition to theoretical predictions, we get an uncomfortable answer: 14.46 billion years, give or take 0.8 billion. The universe itself is 13.8 billion years old, calculated from cosmic microwave background observations with remarkable precision. This star is older than the cosmos that contains it. The error bars technically allow for overlap. 14.46 minus 0.8 billion is 13.66 billion, just barely younger than the universe. But it's an uncomfortable fit, a star that brushes right up against the age of everything. HD 140,283 is a population II star, metal-poor, formed from nearly pristine primordial gas. Its low metallicity confirms it's ancient, one of the first generations of stars born after the Big Bang. The measurements are solid, refined over decades of observation. Either there's something wrong with how we age stars, or something wrong with how we age the universe, or both. The asterisk lithium problem gnaws at our models of Big Bang nucleosynthesis. In the first minutes of cosmic existence, when the universe was hot and dense enough for nuclear fusion to occur everywhere at once, specific ratios of light elements were forged: roughly 75% hydrogen, 25% helium, and trace amounts of deuterium, helium-3, and lithium-7. We can calculate these ratios precisely using the known laws of nuclear physics, the temperature and density of the early universe, and the expansion rate predicted by general relativity. The predictions are remarkably specific, and for decades they've been tested against observations. When we measure primordial gas clouds, regions of space that have never been enriched by stellar processing, helium matches the predictions perfectly. Deuterium matches. Helium-3 matches. Lithium is off by a factor of 3. The universe created only 1/3 as much lithium as it should have, or destroyed 2/3 of what it made, and we don't know why. This is not a small discrepancy or a subtle observational uncertainty. It's a glaring mismatch between theory and reality, a failure of one of the most successful predictions in all of cosmology. Proposed solutions include lithium destruction in stellar interiors, though this requires specific mixing processes that seem contrived. Others suggest the primordial lithium was somehow destroyed by processes in the early universe we don't understand. Still others propose that the nuclear reaction rates we use in our calculations are slightly wrong, or that the expansion rate of the early universe was different than we calculate. None of these explanations are satisfying. Each requires adjusting something we thought we understood, admitting that our model of the first minutes of cosmic time has gaps. These aren't minor discrepancies. They're fundamental challenges to our measurement of cosmic time. If the early universe was hotter or denser than we calculate, if it expanded at different rates, if the physics of nuclear reactions or stellar evolution operates differently under extreme conditions, then everything shifts. Ages change. Distances change. The entire chronology we've reconstructed becomes unreliable. The timeline of cosmic history that we teach in textbooks, that we've built our entire framework on, might be wrong. Not slightly wrong, not in need of minor adjustments, but fundamentally miscalibrated. Time itself might be broken, or at least our measurement of it. The clocks we use to measure the age of stars, the age of galaxies, the age of the universe itself, may be ticking at the wrong rate. And if we can't trust our clocks, how can we trust any of our conclusions about cosmic history? Dark matter is failing tests. We built entire models around something we've never seen. Dark matter is supposed to be the scaffolding of the universe. An invisible substance that outweighs ordinary matter by a factor of 5, dark matter provides the gravitational glue that holds galaxies together, the framework on which cosmic structure forms. Without it, galaxies would fly apart, clusters would dissolve, the cosmic web wouldn't exist. The evidence for dark matter is overwhelming. Galaxy rotation curves show that stars orbit galactic centers too quickly to be held by visible matter alone. Gravitational lensing maps show invisible mass-bending space around galaxy clusters. The cosmic microwave background contains patterns that require dark matter to explain. Structure formation simulations only work when dark matter is included. For decades, the cold dark matter model has been astoundingly successful. It predicts the large-scale structure of the universe, the distribution of galaxy clusters, the patterns in the cosmic web. At large scales, dark matter works beautifully. At small scales, it's failing. The asterisk missing satellites problem has haunted cosmology for over 2 decades. When we simulate the Milky Way's dark matter halo on computers, we find that it should contain thousands of small dark matter subhalos, each potentially hosting a dwarf galaxy. These are the prediction of cold dark matter models, the natural outcome of hierarchical structure formation. We find dozens, not thousands, dozens. The Milky Way has about 60 known satellite galaxies, most of them dim dwarf spheroidals barely visible against the background sky. Surveys keep finding more, pushing into fainter and fainter regimes, but we're nowhere close to the thousands predicted. Where did they go? Did they never form? Were they somehow destroyed? Do they exist but remain invisible, dark matter halos with no stars? Every explanation requires tweaking the properties of dark matter or invoking new physics. Maybe dark matter is warm instead of cold, moving fast enough to smooth out small-scale structure. Maybe feedback from early star formation blew the gas out of these small halos, preventing star formation. Maybe reionization heated the gas enough to prevent it from falling into small dark matter halos. Each solution creates new problems. Warm dark matter alters large-scale structure predictions in ways that conflict with observations. Stellar feedback strong enough to empty thousands of halos would leave other signatures we don't see. Reionization can prevent star formation in low-mass halos, but it can't explain the sharpness of the cutoff. Then there are the *** galaxies with no dark matter at all ***. NGC 1052 DF2 made headlines when observations revealed it rotates too slowly for its visible mass, containing little to no dark matter in its halo. This shouldn't be possible. In the standard model, galaxies form in dark matter halos. The dark matter collapses first, creating gravitational wells into which gas falls and forms stars. You can't have a galaxy without dark matter, any more than you can have a shadow without something casting it. Yet NGC 1052 DF2 exists, and it's not alone. Its companion NGC 1052 DF4 shows similar properties. These are large, diffuse galaxies, but they're not being torn apart by tidal forces or showing signs of disturbance. They're just galaxies that seem to have forgotten to form their dark matter halos. Explanations involve tidal stripping, the idea that these galaxies once had dark matter but lost it through gravitational interactions with nearby massive galaxies. But the stripping has to be so efficient, so complete, that it removes essentially all the dark matter while leaving the stars intact. The mechanism exists but seems contrived. Primordial black holes offer a fundamentally different approach to dark matter. What if dark matter isn't exotic particles at all, but simply black holes formed in the first fraction of a second after the Big Bang? Quantum fluctuations in density could have created regions dense enough to collapse directly into black holes before the universe expanded and cooled. These primordial black holes would be invisible, detectable only through their gravitational effects, explaining both the missing mass and the difficulty of finding it. They would cluster like dark matter, providing the scaffolding for structure formation. They could come in a range of masses, from microscopic to stellar. The idea is elegant, explaining dark matter without requiring new particles or forces. But detecting primordial black holes is nearly impossible. They don't emit light. They don't interact except through gravity. We can search for their gravitational effects, their lensing signatures, the slight brightening of distant stars as a primordial black hole passes in front. But the searches are slow, limited by statistics and observational constraints. Some evidence exists. Gravitational wave detections from LIGO show black hole mergers with unexpected mass distributions. Some of these might be primordial black holes rather than black holes formed from stars. But the data is ambiguous, open to interpretation. Modified gravity theories like MOND, modified Newtonian dynamics, suggest we don't need dark matter at all. Perhaps gravity simply behaves differently at galactic scales, following equations we haven't discovered yet. Instead of Einstein's general relativity, perhaps there's a more complete theory that reduces to general relativity in strong fields but deviates in weak fields. MOND successfully predicts galaxy rotation curves with remarkable accuracy. Give it the distribution of visible matter in a galaxy, and it predicts how fast stars should orbit. The predictions match observations better than dark matter models in many cases. This is not a trivial success. Rotation curves are precisely the problem that inspired dark matter in the first place. But MOND fails at larger scales. It cannot explain gravitational lensing by galaxy clusters without invoking some form of invisible matter. It struggles with the cosmic microwave background, with structure formation, with the detailed observations that dark matter handles effortlessly. It's a theory that works brilliantly in one regime and fails in another. Perhaps the truth is somewhere between. Perhaps there's some dark matter, less than we think, and gravity is modified at certain scales. Perhaps dark matter is more complex than we imagine, interacting with itself or with ordinary matter in ways we haven't detected. Or perhaps our entire framework is wrong, and we need a more radical rethinking. The uncomfortable reality is that we've built an entire cosmology on a foundation we've never seen. Dark matter makes up 85% of the matter in the universe, yet we've never directly detected a single dark matter particle. We infer its existence from its gravitational effects, construct elaborate theories about what it might be, build massive detectors deep underground to catch its faint interactions with ordinary matter. And we find nothing. Detector after detector, experiment after experiment, comes back empty. The non-detections pile up, constraining the properties dark matter can have, shrinking the parameter space where it could hide. It should interact at least occasionally with ordinary matter. It should annihilate with itself, producing gamma rays or other signatures. It should clump in the cores of galaxies and the sun, creating detectable signals. We see none of this. Dark matter remains stubbornly invisible, present only in its gravitational effects, silent in every other wavelength and interaction. And as the missing satellites problem, the galaxies without dark matter, and the failures of direct detection pile up, we have to wonder, are we chasing something that doesn't exist, or are we just looking for it in the wrong way? The universe turned on too early. Something lit the cosmos before stars could. Between about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. And about 200 million years later, when the first stars ignited, the universe was dark. This period is called the Dark Ages, a cosmic midnight between the afterglow of the Big Bang and the dawn of structure. The universe during this time was filled with neutral hydrogen, cold and dark, absorbing any light that might pass through it. The first stars had not yet formed. No galaxies existed. The cosmos was a vast darkness, cooling and expanding, waiting for gravity to gather enough gas together to ignite the first nuclear furnaces. The asterisk epoch of reionization should mark the moment when this darkness ended. As the first stars formed and began to shine, their ultraviolet radiation ionized the neutral hydrogen around them, carving bubbles of transparency in the cosmic fog. These bubbles grew and merged as more stars formed, eventually ionizing all the hydrogen in the universe. This should have happened gradually, over hundreds of millions of years, as population III stars formed and died, as the first galaxies assembled and filled space with their light. The timeline is clear. First stars at 100–200 million years, reionization complete by about 600–800 million years. Instead, reionization happened too early and too quickly. Observations of distant quasars, whose spectra show complete ionization at redshifts corresponding to 400–500 million years after the Big Bang, indicate the universe was already flooded with ionizing radiation. The timeline doesn't work. There weren't enough stars yet. The first galaxies were just forming. The universe was flooded with ionizing radiation when it should have been dark. The first stars cannot account for the energy required. We can estimate the number of stars needed to ionize the universe by calculating the total energy required and dividing by the energy output of a typical massive star. The numbers don't add up. There simply weren't enough of them, and they weren't bright enough. Unknown energy sources must have contributed. Primordial black holes asterisk, if they exist in sufficient numbers, would accrete surrounding gas and radiate enormous amounts of energy. The accretion disks around small black holes could have been incredibly bright, flooding space with ionizing photons. Dark matter annihilation asterisk offers another possibility. If dark matter particles can annihilate with each other, they release energy. In the dense early universe, dark matter would have been concentrated enough for annihilation to occur frequently. If these annihilations produced photons energetic enough to ionize hydrogen, they could have contributed significantly to reionization. Or perhaps something else entirely, a phenomenon we haven't even theorized yet. Unknown sources of energy in the early universe, processes that occur only under the extreme conditions of cosmic dawn, mechanisms that stop operating once the universe expands and cools below critical thresholds. The observations keep getting more puzzling. JWST has detected ionized regions at redshifts corresponding to just 300 million years after the Big Bang, pushing the timeline even earlier. Some observations suggest ionization might have begun even before this, driven by sources we cannot identify. Something lit the cosmos before the first dawn, and we don't know what it was. In the darkness before stars, the universe was already glowing, filled with energy from sources our models don't include. Either the first stars were radically different from our predictions, far more numerous and far more powerful, or something else was out there in the darkness, generating the light that ended cosmic midnight. The implications extend beyond just reionization. If the early universe had energy sources we don't understand, those sources could have affected structure formation, galaxy evolution, the growth of black holes. They could have left imprints on the cosmic microwave background, altered the distribution of matter, changed the course of cosmic history in ways we haven't recognized. Every assumption we make about the early universe rests on understanding what processes were operating, what sources of energy were available. If we're missing major contributors, if significant energy sources remain unidentified, then our entire reconstruction of cosmic history becomes suspect. The Great Silence. In a universe this old, silence is the strangest signal of all. The Fermi paradox is less a mystery and more an accusation. It begins with simple math. Our galaxy contains somewhere between 200 and 400 billion stars. Current estimates suggest that nearly all of them have planets. A significant fraction of those planets orbit in habitable zones where liquid water could exist. Even conservative estimates put the number of potentially habitable planets in the billions. Our galaxy is 13 billion years old. The oldest stars, those formed from nearly pristine primordial gas, are almost as old as the universe itself. Life on Earth arose relatively quickly, appearing in the geological record within a few 100 million years of conditions becoming suitable. If Earth is typical, then billions of planets have had billions of years for life to arise, to evolve, to develop intelligence and technology. Advanced civilizations should be common. We should see evidence everywhere. Megastructures harnessing stellar energy, electromagnetic signals broadcasting across the galaxy, evidence of astroengineering projects, artifacts, probes, the unmistakable fingerprints of intelligence operating at interstellar scales. Instead, we find nothing. The electromagnetic spectrum is quiet. Space is empty of beacons. The galaxy shows no signs of engineering at cosmic scales. We point our telescopes at thousands of star systems and detect no artificial signals, no evidence of technology, no signs that anyone else is out there. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" The question has haunted SETI researchers and cosmologists for decades. With so many opportunities for life, intelligence, and technology to arise, why do we appear to be alone? Perhaps we're the first. Perhaps intelligence is so rare, requiring such an unlikely sequence of events, that we're the only technological civilization in the observable universe. This is the rare Earth hypothesis, the idea that while simple life might be common, the specific sequence of events that led to complex life, multicellularity, intelligence, and technology on Earth is so improbable that it almost never happens elsewhere. The hypothesis sounds like special pleading, like anthropocentric thinking. But when you list the specific requirements, a star of the right mass and metallicity, a planet in the habitable zone, a large moon to stabilize the axial tilt, a magnetic field to protect the atmosphere, plate tectonics to recycle nutrients, Jupiter-sized planets in outer orbits to deflect asteroids, mass extinction events to clear ecological niches for new species, the probability multiplies into vanishingly small numbers. Perhaps we're not looking correctly. Advanced civilizations might not use electromagnetic radiation to communicate. They might have moved beyond radio and television centuries ago, adopting technologies we can't detect or imagine. They might communicate through gravitational waves, through neutrino beams, through quantum entanglement, through modulated dark matter streams. We're listening to the electromagnetic spectrum like someone trying to catch smoke signals in a world that's moved on to fiber optics. Or perhaps the galaxy is teeming with life and intelligence, but nobody's broadcasting. The universe is too dangerous. Civilizations that announce their presence attract attention, invite conflict, get destroyed by something we haven't encountered yet. So everyone stays quiet, listening to the darkness, afraid to light a beacon. This is the dark forest hypothesis, borrowed from Liu Cixin's science fiction, but increasingly discussed in serious astrobiology circles. The Great Filter ** offers a darker explanation. Something prevents civilizations from spreading across the stars. Somewhere between the origin of life and the colonization of galaxies lies a barrier, a challenge so difficult that almost no one passes it. This is the Great Filter, and its location determines our fate. If the filter is behind us, something about the origin of life, the evolution of intelligence, or the development of technology is so improbable that we're among the first to achieve it. Life might arise rarely. Intelligence might develop rarely. Tool use and language might be rare. This would explain the silence. We're early or lucky or both. If the filter is ahead of us, waiting, then every civilization that reaches our level of development encounters it and fails. Perhaps nuclear war is inevitable. Perhaps artificial intelligence always turns against its creators. Perhaps there's something about expansion into space that we haven't discovered yet, some unavoidable catastrophe that wipes out every species that tries. The fact that we see no evidence of other civilizations suggests the filter is powerful and universal. If even a tiny fraction of civilizations survived it and expanded, we should see them. The galaxy is old enough that even slow expansion, traveling at a fraction of light speed, would fill the entire Milky Way in a few million years. Yet we see nothing. The silence suggests extinction. It suggests that something about intelligence or technology or expansion into space carries a hidden cost, a trap we haven't noticed yet. Every species that reaches our level encounters this trap and falls into it. The great filter is not just difficult, it's nearly insurmountable. Or perhaps the explanation is even stranger. Perhaps advanced civilizations transcend, moving into higher dimensions or virtual realities, so compelling that physical expansion becomes irrelevant. Perhaps they upload themselves into computational substrates, achieving immortality and unlimited experience without ever leaving their home star. Perhaps the endpoint of intelligence is not galactic empire, but inner space, consciousness exploring itself rather than the cosmos. The fact that we hear nothing might be the most important warning in the universe. It might be telling us that reaching for the stars carries risks we don't yet see, that something awaits us in the darkness between stars, that the filter is ahead and not behind. In a universe this old, this vast, this full of stars and planets, silence is the strangest signal of all. And the longer it persists, the more disturbing it becomes. Signals we still can't explain. On August 15, 1977, at 23:16 Eastern Standard Time, the Big Ear Radio Telescope at Ohio State University detected something that should not have existed. A narrowband radio signal, dramatically stronger than background noise, lasting exactly 72 seconds, coming from the direction of the constellation Sagittarius. The signal swept through the telescope's beam as Earth rotated, rising from background noise, peaking at 30 times the baseline level, then fading back to silence. Astronomer Jerry Amon was reviewing the computer printout 3 days later when he noticed the spike in intensity, circled it, and wrote "Wow" in the margin. We've never heard it again. The asterisk "Wow" signal asterisk matches exactly what we'd expect from an artificial transmission. It occurred at 1420 megahertz, the frequency of neutral hydrogen's emission line, known as the water hole, in SETI circles because it's where the galaxy is naturally quiet. The bandwidth was narrow, about 10 kilohertz, the kind of tight beam an artificial transmitter would produce. Natural radio sources are broadband, spreading their energy across wide frequency ranges. This was focused, deliberate, targeted. The signal came from right ascension 19 hours 25 minutes, declination minus 26 degrees, an empty region of space between star groups Chi Sagittarii and Tau Sagittarii. Follow-up observations found nothing. The Big Ear Telescope returned to that region of sky multiple times over the following months and years. Other radio telescopes pointed at the coordinates. Every search came back empty. Explanations involving Earth-based interference have been proposed and largely ruled out. The signal's narrow bandwidth and specific frequency are wrong for terrestrial transmitters. Satellites operating at that frequency were tracked, and none passed through the beam. Military aircraft, radar installations, ground-based transmitters, none match the characteristics. A 2017 paper suggested the signal might have come from a comet, specifically comets 266P/Christensen and P2008Y2, which were in the vicinity at the time. Comets carry clouds of neutral hydrogen that could emit at 1420 megahertz, but the hypothesis has problems. The signal was too strong, too narrow, too brief. Cometary hydrogen clouds emit continuously, not in 72-second bursts. And the comets weren't quite in the right position. The signal remains unidentified, unrepeated, unexplained. It sits in the archives as the best candidate for an artificial extraterrestrial signal we've ever detected, but without a second occurrence, it proves nothing. One data point is an anomaly. 2 data points is a pattern. Without repetition, the wow signal remains tantalizing but scientifically inconclusive. Fast radio bursts appear across the cosmos with disturbing frequency. These are millisecond-long pulses of radio energy, each releasing as much power as the sun emits in days or weeks, compressed into a time span shorter than a heartbeat. The first was discovered in 2007, buried in archival data from the Parkes telescope. For years, they were considered rare cosmic accidents, cataclysmic one-time events. Then we found repeating FRBs, sources that flash again and again. FRB 121102* was the first repeater discovered, a source that pulses irregularly but persistently, allowing astronomers to pin down its location in a dwarf galaxy 3 billion light-years away. The existence of repeaters changed everything. FRBs weren't one-time cataclysms. They were emissions from something that survived, something that could generate these bursts repeatedly. Some repeaters show *** periodicity **, suggesting rotation or orbital motion. FRB 180,916 * pulses in a cycle, active for 4 days, silent for 12, then active again. The precision is unsettling, the regularity too perfect. Other repeaters like FRB 121,102 flash seemingly at random, with no discernible pattern, but statistical analyses hint at underlying structures in the timing. Natural explanations exist. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, can generate FRB-like emissions through magnetic reconnection events or crust quakes. Neutron star collisions, though they should be one-time events, might explain some bursts. Exotic physics involving black holes, strange quark matter, or primordial objects from the early universe have been proposed. But the patterns are unsettling. The precision of repeating FRBs, the specific characteristics of their bursts, the way they cluster in certain regions of the sky. Some FRBs show downward frequency drift, the signals starting at higher frequencies and sliding lower over milliseconds. Others show multiple subbursts within a single FRB, structured pulses that look designed rather than random. The debate between artificial and natural origins continues, usually in hushed tones because suggesting artificial origins invites ridicule. Science requires extraordinary evidence for extraordinary claims, and proposing that FRBs might be technology without proof invites dismissal. But the characteristics keep accumulating: narrow bandwidths, structured pulses, periodic repetition, astronomical energies focused into tight beams. If FRBs are natural, they represent physics at extremes we barely understand. If they're artificial, they represent technology operating at power scales we can barely imagine. Either way, they're telling us something important about the universe. Each new FRB adds data but rarely clarity. We've detected hundreds now, cataloged their properties, traced some to specific host galaxies. The more we learn, the stranger they become. We're listening to something we don't understand, something that operates on timescales and energies our theories barely accommodate. And there's another possibility, one that keeps astronomers awake at night. Maybe we're detecting the echoes of conversations we're not meant to hear. Maybe FRBs are the leakage from communications between civilizations operating at energies and distances where inefficiency doesn't matter. Maybe we're eavesdropping on a galaxy that's far less empty than it appears. A star that shouldn't exist. Tabby's star ** flickers in the constellation Cygnus like a dying light bulb, 1,470 light-years from Earth. Its official designation is KIC 8,462,852, a designation it earned as target number 8,462,852 in the Kepler Space Telescope's survey of stars. For most of its observation period, it appeared utterly normal. Then something moved across its face, blocking its light. The dips were unprecedented. Most exoplanets cause their stars to dim by about 1% as they transit across the stellar disk. Jupiter, the largest planet in our solar system, blocks about 1% of the sun's light when it passes in front. Tabby's star dimmed by 22%. Something enormous was blocking its light, something much larger than any planet. The dimming events were irregular, unpredictable. Some lasted days, others weeks. Some dips were shallow, others profound. The light curves showed complex structures, multiple dips within single events, asymmetric profiles that suggested multiple objects or something with irregular edges. The light dips are asymmetric, suggesting solid objects rather than spherical bodies. When a spherical planet transits a star, the light curve is smooth and symmetric, rising and falling in a characteristic pattern as the planet moves across the disk. Tabby's star's dips are jagged, irregular, showing sudden changes in brightness that suggest occulting objects with complex shapes. The dimming events don't repeat on predictable schedules. If a planet or group of planets were responsible, we'd see regular transits, eclipses occurring at fixed intervals as the objects orbit the star. Instead, the dips appear random, clustered in groups, separated by long periods of normal brightness. Whatever's blocking the light doesn't follow simple Keplerian orbits. Citizen scientists poring over archival data discovered that Tabby's star has been dimming overall, fatting by about 20% over the past century. This long-term dimming suggests something is accumulating around the star, building up over decades, gradually obscuring more and more light. Comets have been proposed as an explanation. A family of comets in highly eccentric orbits, breaking apart as they approach the star, creating clouds of dust and debris that occult the light. Comet fragments can be large, irregular, capable of causing deep and complex transit signatures. The scenario is plausible but requires fine-tuning. You need a lot of comets, breaking apart at just the right times, in just the right orbits. The comet hypothesis struggles with the long-term dimming. Cometary dust should disperse relatively quickly, blown away by stellar radiation pressure. Maintaining a steady dimming trend over a century requires continuous replenishment, a steady stream of comets breaking apart year after year. The numbers become difficult to justify. Other explanations have been attempted. Maybe the star swallowed a planet, the disruption creating clouds of debris that are still settling. Maybe there's a disk of material around the star, seen nearly edge-on, with clumps and gaps that cause irregular dips. Maybe the star itself is variable, exhibiting pulsations or instabilities we don't fully understand. Each hypothesis is tested against new data and found wanting. The dimming patterns don't quite fit stellar variability. The disk scenario requires specific geometries and compositions. The planetary disruption should have left other signatures we don't see. And then there's the unspoken possibility, the explanation whispered in conference hallways and late-night discussions, but rarely put in print: a megastructure. A Dyson swarm under construction. An array of solar collectors, habitat rings, computational substrates, orbiting the star in complex patterns, harvesting its energy. Panels and collectors of different sizes and orbits, occasionally passing in front of the star from our perspective, blocking its light in irregular patterns as construction continues. It's the explanation no one wants to voice too loudly, the interpretation that sounds like science fiction, the hypothesis that invites ridicule from colleagues and sensational headlines from media. But it fits. It explains the irregular dips, the long-term dimming, the asymmetric light curves. It explains why the patterns don't follow simple astronomical models. A megastructure wouldn't orbit like a planet. It would be composed of thousands or millions of individual components in different orbits, different configurations. It would block light irregularly, creating complex signatures that change over time as the structure grows. It would cause long-term dimming as more collectors are added, accumulating over years and decades. The hypothesis is taken seriously enough that SETI observations have been conducted, radio telescopes pointed at Tabby's star, listening for artificial signals. So far, nothing. But absence of evidence is not evidence of absence, and a civilization capable of building megastructures might communicate in ways we can't detect. Natural explanations continue to be developed, refined, tested. Each new observation of Tabby's star adds data, constrains possibilities, eliminates hypotheses. But the star remains anomalous, defying simple categorization, suggesting that either we're missing something fundamental about stellar physics or we're watching something unprecedented. There are other candidate stars now, other objects showing similar behavior. Pleiadian star is no longer alone. VVV-WIT-07**, J1407**, and several others show irregular dimming patterns, deep transits, complex light curves. The phenomenon might be more common than we thought, or we're simply getting better at detecting it. But Tabby's star remains the prototype, the star that started the conversation, the object that forced astronomers to consider possibilities they'd dismissed. It sits there, 1,470 light-years away, flickering irregularly, blocking its own light with something we cannot explain. And sometimes, late at night, when you're alone with your thoughts and the data, you can't help but wonder, what if we're watching something being built? What if the dips in brightness are shadows, cast by structures beyond our capability, projected across space for us to see? What if someone out there is building their future, and we're fortunate enough to witness it? The star keeps flickering, we keep watching, and the mystery deepens. Every generation believes it understands the universe. And every generation eventually learns it doesn't. We thought the Earth was the center of everything, then learned it wasn't. We thought the Milky Way was the entire universe, then discovered billions of galaxies beyond it. We thought the universe was eternal and unchanging, then discovered it's expanding from a finite beginning. Each revolution in understanding revealed a cosmos stranger and grander than we'd imagined. Each discovery pushed the boundaries of reality farther out, expanded the scope of what's possible, humbled our assumptions. These 50 mysteries are the next wave. They're cracks in our current understanding, anomalies that don't fit, observations that challenge our best theories. They're uncomfortable because they suggest our framework is incomplete, that the equations we trust might be missing variables, that the story we tell ourselves about cosmic history might be wrong. Maybe these mysteries aren't errors. Maybe they're not problems to be solved, but signals to be interpreted. Maybe they're invitations, pointing us toward deeper truths, stranger physics, more profound understandings of reality. The cold spot and axis of evil suggest the early universe had structure we can't explain. Dark flow and the great attractor suggest the universe has geography beyond our horizon. The giant arc and aligned quasars suggest space itself remembers, preserves correlations, maintains patterns across impossible scales. The mature galaxies JWST sees suggest time ran differently in the early universe, or our clocks are miscalibrated. The missing satellites and galaxies without dark matter suggest our most successful theory is incomplete. The early reionization suggests energy sources we haven't identified. The great silence suggests filters we haven't passed or futures we don't understand. The wow, signal and fast radio bursts suggest signals we can't decode. Tabby's star suggests phenomena we can't categorize, possibilities we're afraid to voice. Each mystery stands alone, explainable perhaps through unknown physics, statistical flukes, observational errors. But together, they form a pattern. Together, they suggest that something fundamental about our understanding is wrong. Not slightly off, not in need of minor adjustments, but fundamentally miscalibrated. Maybe the universe isn't broken. Maybe our models are. Maybe we've built an elegant structure on a foundation with cracks we haven't noticed. And these mysteries are where the cracks show through, where reality leaks around the edges of our equations. The universe is under no obligation to make sense to us. It doesn't care about our theories, our models, our carefully constructed frameworks. It simply is, operating according to rules we're still learning, exhibiting behaviors we're still cataloging, revealing depths we're still discovering. Perhaps that's the real message of these mysteries: humility. The recognition that we're still early in our understanding, still students in a cosmic classroom, still learning the basic vocabulary of a language spoken in mathematics and light. The universe is deeper than our current knowledge, stranger than our current imagination, more complex than our current models can hold. And that's not a failure, that's an opportunity. These mysteries are not endpoints but invitations, not walls but doorways, not problems but puzzles, waiting for the next generation of thinkers to approach them with fresh eyes, new tools, different perspectives. Somewhere in these 50 mysteries lies the seed of the next revolution in physics, the next fundamental insight that will rewrite our understanding as completely as Einstein's relativity rewrote Newton's mechanics. We don't know which mystery holds that seed. We don't know what form the solution will take. We don't know who will solve it or how long it will take. But the mysteries are there, persistent and real, carved into the cosmos, waiting. Reminders that reality is deeper, stranger, and far less finished than we imagine. Good night.